Okay, so thank you all very much for attending. I'm going to just take like a minute just to orientate us. I hope you've all read this. Why we're having this session, to receive input on research, to discuss and identify key research questions, and to potentially set up a national extreme climate event working group. Here's a set of questions which we can revisit later. You know the order. We're starting off with Saul's presentation. We have 2 videos after that for people that will be online remotely, but we've got their videos of their presentation. Jimmy's is, I think, 18 minutes, and Izzetdien's is 14 minutes. Then Abu Bakr will present. We're going to have lunch. Then we've got Mary Jane, who's going to be our guest speaker. Then we've got Mabui. I don't know what the first name is. Then Caitlin, then Wanjiru, then Nicole, and then Vuyo. Now, I think that there's a team break between Nicole and Vuyo. Then we're going to do a group exercise to respond to these questions that I've set up. And then we're going to have a short panel discussion and an open discussion around this. So you will all have received a piece of paper, which again, it's not obligatory, but if you feel that you have something you want to contribute, you can read that and answer those questions in the cards. If we run out of cards, just write on the back of the piece of paper, and we can use those later. And then just to mention that tomorrow we have another session looking at climate and health in particular. There's some changes there. So that is the orientation. I don't want to say too much more other than you heard this morning's talk from Francois Engelbrecht, and that's why we are very glad to count his talk as part of our session, which we did there. And so without further ado, you can commence with the program, and we have a joint presentation. This is in fact a guest speaker slot from our co-sponsors. I could say that this project, emerges out of an NRF project called APEX, which is looking at extreme events. SAWS, UP, Zululand, Limpopo, and Wits are part of this. And as SAWS, co-host and co-organizing this with us, with Charlotte, who will take the floor now. Thank you, Charlotte. I'll fill up your report. So there. There's the microphone. Not how you working.
No, yeah. Never mind.
All right. Thank you.
Sit up.
I'm going to sit over here.
Good morning, everyone. It's a real privilege to be with you this morning, talking about extreme events. And I think this talk is nicely on from Francois' opening session. I've got quite a few slides, so I'm going to talk really quickly. So I apologize for that. I saw this morning how Francois really did speak very slowly and lots of time to process. I'm not going to be doing that this morning. The research I'd like to discuss is the research I did with some people I know, Dr. Andries Kruger at the Weather Service and Professor Liesl Dyson. So I'm going to be looking at temperature records that we found, or the breaking of temperature records for South Africa, as well as extreme rainfall characteristics that we found in the non-stationary climate of South Africa. Just a brief overview of my talk as more people come in. It's lovely to see people coming in. There's some more seats here. You can move my laptop and just pop down here. So I'm going to cover the need for the study, the data we used, as well as some methodologies. We'll look at some results and discussion, and then some conclusions. So the need for the study, we found that there was very little in the literature about record-breaking temperature events in South Africa. And then also this conference also highlights that global warming and the associated climate change has significant local effects. And I think listening to some of the speakers over the years today, we really do see that in Africa and South Africa. So it's expected that obviously in a warming climate, we're going to be getting more warm and hot extremes in surface temperatures, and these are becoming more frequent, whereas our cool and cold extremes less so. But how does that translate into the frequency and distribution of rainfall records in South Africa? And then obviously we all know with climate change, this has already affected the intensity of rainfall in many parts of the world, and therefore we thought it appropriate to investigate it in the South African context. Historic and future trends in multi-year extremes could have significant impacts. And this morning we saw those impacts in parts of the world and ours, and therefore we need a better understanding of these events. So what data do we use? We use near-surface homogenized temperature data from the South African Weather Service for our temperature data sets, and those are the red dots. So well distributed across South Africa. The time series of the data is from 1951 to 2019. And then for the rainfall or precipitation study, we use 70 stations, and they are a data set from 1921 to 2020. So what kind of methodologies did we use? Well, for the temperature one, we obviously defined a breaking record as the highest or lowest than any previous max or min in the time series for that particular weather station. And then the number of records we counted, and we compared, say, the 1st of January with all subsequent Januaries in the time series. And then in a stationary climate, the theoretical or expected number of records is 1/n, and Pan et al. 2013 did some work around explaining why that is. But because we know that the climate is not stationary impacted warming, we also made in the study provision for the warming trend, and I will discuss that a bit later. And then the student t-test was used to evaluate the statistical significance of the difference at 5% confidence limit between the linear trend in the time series of years prior to and after the years. How did we look at the methodology for the precipitation study? So it was an interesting study where we were able to split the series into two 50-year periods, 1921 to 1970, and then 1971 to 2020, and then we could really look at the difference. Based on the literature, we defined extreme or very heavy daily rainfall as daily rainfall events over 50 mils, 75 millimeters, and 115 millimeters. And then using the gamma distribution, we had a look at the daily rainfall general distribution to see if there were any changes between period 1 and 2 for each of the rainfall stations in the study. Due to the fact that extreme rain values occur more than once in the year, we use the peak over threshold method to investigate as well, because sometimes in dry years, your rainfall isn't very high. So when we use a peak over threshold, we take all rainfall values above a threshold and put them into the distribution for peak over threshold. So we did some work around that. And then we calculated return periods for the 1 in 10, 1 in 50, and 1 in 100-year period for each of those using this method. The Anderson-Darling test was then used to look at the difference, and this is a test that looks particularly at the tails of the distribution, so it's quite a good statistical test in terms of having a look at the 95% confidence limit and how confident we are that there is a significant change. And then return periods estimated for those predefined extreme 50 mils, 75 mils, and 115 mils. So what were some of our results? Well, our results were quite interesting. The top two graphs or maps. So on this side, sorry, I don't have a pointer, I'm going to use my mouse. So on these are all looking at your high T max and your high T mins on this side of the slide. Over here, we just took a look at the trend. So where you're looking at your dark colors, the red, that's where we're going to expect to find more records. And when we put that trend into the data, these are the areas, again, the darker colors, the darker pictures are where and here where we are expecting the records to be greater than the rest of the country. But what did we find? Well, having a look here at the T max temperatures, you can see that it actually gets very red over the center of the country. And those stations are doubling. And this is just for the last 10 years of the study, for 2009 to 2019. We get a double in the observational record of what was expected. So in a 10-year period, you can expect, if you've got a data series from 1951, you're expected in a non-stationary climate to get 6 records per year. In this slide at the bottom, in these dark colors over the central parts of the country where we are situated today, you're looking at over 20. So that's quite something. And then if you have a look at your T-min records, it's a different distribution of spatial pattern. So that was very interesting for us in terms of the fact that where you're breaking high max records, you don't necessarily follow on that you're going to be breaking in a similar area T-min records. So then what we did is, if you have a look at the top graph, once again, on this side of the slide, you're getting your T-max and your high T-mins. If you have a look at this graph, I'm sorry for the people at the back that you can't really see what's going on, but this light gray line is the 1/n, so that is what you're expecting in terms of the number of records as you move through the data series. And then the black line are the actual observed records. And you can see with these circles, the peaks. So you're getting peaks of records, and then the following year, you're getting less records, peaks again, and less records. So that was quite interesting in terms of that it's not just a straight increase in the number of records. Towards the end of the analysis period in the T-max, you're seeing a great jump in the number of records when you take into consideration all the stations in that time series. The student t-test for the difference between before and after every year in the study was done to find out if there were any abrupt changes in the mean. And this is what these two graphs in the middle of the slide are showing. So these abrupt changes in the mean are happening at these areas that I've highlighted with the circle. So the highest absolute value of the test indicates the year at which the mean before and after a specific year is most significant. For the annual average T-max, this was around 1997, and for the T-min, it's 1982. And there were other years that were also shown by those circles. Going on to the bottom part of the two graphs, this is the 30-year annual mean T-max, T-min temperature trend for all the stations. It's significant at the 5% level. And once again, that trend isn't a continuous trend, it changes. So the abrupt changes in the mean in your C and D here, C and D graph here, actually where the abrupt changes in the temperature trend occurred, in the following year after that abrupt change, the number of records are higher than the general trend in the frequency of the occurrence of these records, as seen in A and B. These abrupt changes in the mean and in the temperature is the cause, we think, for the high number of T-max and T-min records the following year. So if we have a look at this slide, this is a very interesting slide to investigate the acceleration of the trend and whether this can explain the anomalous large number of T-max records over the last decade. So the trend was adjusted for each decade according to the average trend over the previous 30 years. The figure represents the expected annual average number of records over the previous decade in the case of no trend, and that is the blue line. So the blue line is no trend, and we've extended that with the dots to the year 2040. And then you're getting the trend of the orange line, which is 0.2 degrees C per decade. And that's the orange line, and then the variable trend, which is for the last decade, 1.34 degrees, and that's the gray line up at the top there. And then the yellow line indicates the observed number of records, and you can see that that actually coincides much more with the variable trend in the temperature record. So we are thinking that that is explaining why we're getting these records. It's actually because of the non-consistency of the trend. So looking at the rainfall study, you've got period 1, 1921 to 1970, like I said, on this side of the screen. And then on this side of the screen, you're getting the second period, 1971 to 2020. And then this is the difference between those as a ratio. So what we're seeing across the country is that most stations, you can see, are receiving more than 50 mils of rain per day, not per every day, but the probability of receiving above 50 mils of rainfall on a rainy day is estimated with the Gummo distribution. And where these differences are, the dark colors are showing where in this period, those are significantly increasing. The lighter color, where actually in period one, you're getting more of those 50 mils. So in fact, these lighter colors are drying out. Then I mentioned the peak over threshold method. So this is when we're taking into account all the extreme rainfalls, and we did those return periods. The 1 in 10 is at the top, 1 in 50 in the middle, and 1 in 100 at the bottom. First period, second period, and the difference as a ratio. You can see that the pattern of difference between those three return periods is very similar. And what you can, if you were paying attention to Francois' presentation, will be alerted to is this area over here where we're thinking in all three periods that there is a shortening of the return period or an increase, in the rainfall expected in these periods. So you're getting more rainfall occurring in these periods for your return periods. So the difference between return period 1 and 2 is a ratio, and you can see these are the larger estimations in these parts of, even in this part of the country as well. So if we have a look at return periods and we translate that into the receiving of 50 mils, 75 mils, and 150 mils, you can see once again the first period here, the second period here, and then the difference as a ratio. Interesting, in the 50 mils, there was only one station in the first period that had return periods of 50 mils, and that was Mount Edgecombe. When we move to the second period, so that's the grey, you can see most of the stations over KwaZulu-Natal and over this part of the eastern parts of our country obviously are expecting. So that's quite a big change. You can see it reflected here, and over these areas we're also getting a big difference in terms of return periods of 50 mils, and that return period is shortening. 75, most of the country you can see is changing. The white areas in all of these maps are where it was the first period had these return periods that are larger than the second lot of periods, but you can see a general pattern over this part of the country. And I think that this is quite scary in terms of what Francois was saying, in terms of these areas are now looking to experience these types of rainfall events more rapidly. And if I go back to this slide over here, these colors in the second period for your 1 in 100 year return periods are looking at values over 600 mils in a day. We didn't get that if you were listening to Francois' talk this morning at those kinds of values, but that is what we are having a look. That's what the data is saying, that those return periods are looking, and this is observed data. This isn't future projection data. This is actually what the frequency distributions are saying, that those areas 1 in 100 years millimeter could be sitting at something like 600 mils over Letaba and Mount Edgecombe. So that's quite scary stuff. The conclusion, the frequency of breaking temperature records deviates from the expected frequency. The distribution of record temperatures was affected by the warming trend, and this warming trend is not linear and is improving in later years. This study also found that the distribution patterns between the occurrence of T high max and T min records was different. And we also think that these record-breaking temperature events can serve as an indication of climate change. Record temperatures should change the multi-year extremes, so the 1 in 50 return period, which should have a bearing on assessing the impact of climate change on relevant socioeconomic sectors, especially those that are vulnerable to these types of events. Our research also indicates that the frequency and intensity of extreme rainfall events across South Africa is increasing. These spatial distributions of change in both the return period values and return periods indicate that most stations are affected, and thus the changes are not defined to one rainfall region. With the increase in return period values, especially over the eastern parts of the country, where the potential threat of flooding is of concern, with some of these areas said to receive 400 mils for their 1 in 50 return period values. The implications of increase in the magnitude and frequency of high rainfall events is of serious concern. And therefore we have to, as Francois asked the question, how we are forecasting those events, and also how are we making sure that our coping strategies are effective. I'm now going to hand over to my colleague who's going to take the presentation.
For both of them. Unfortunately, chairs, if you prepare to sit on a table or lean up on a table between people, that would be also cool. I don't mind. I will sacrifice my chair for somebody that really wants it, and we'll hand over to Christine. Thank you.
Thanks very much, Noah. Okay, to try and get a flying start, Charlotte has left off. The importance of the observed increases in extreme events. There's no doubt about that. So, and also after this morning talk of the importance of early warning to enable or to make it possible to take people out of the danger zones, and also in other sectors, let's say the agricultural sector, mitigation strategies for hot seasons. That is now what we're going to focus on in the remainder of this source talk. So how can we predict it? Well, actually, it's easy to predict events, but is it really useful? How far in advance can one really predict extreme events? So now, for the remainder of the source talk, we're just going to look at the prediction of extreme temperatures and focusing on the subseasonal timescale. So we now know our short range timescale is a few days ahead, then there's a medium range timescale up to about 10 or 14 days, and then after the 2-week period, up to about 2 months into the future, referred to as a subseasonal timescale. And that is a timescale that is inherently very difficult to predict. Okay, so now looking at extreme temperatures. So just starting off here with an animation of the seasonal cycle of heatwave days. And yeah, I think it starts in September. That's the end of the summer season. Let's just go there's September. Now it will animate the monthly frequency of heatwave days up till March. So basically the message here is, I think that you can see that over the central, more or less over the central parts of the country, is the part of the country where extreme temperatures, defined here as heatwave days, occur most frequently. So that is kind of a danger area, or area to be, to know of where things like extreme temperatures can really have an impact. As we've seen in this past heatwave event, where farm workers died as a result of its risks over that central western part of the country. Okay, this slide here is just to remind us that here over Southern Africa, we really, climate change or not, our climate is variable. That is from year to year, that is also within the season. On this slide here, what we are just trying to show is the occurrence of heatwave days within the summer season. And the summer season we have defined as from the 1st of October till the end of March. Let's say 1st of October 2021 till the 31st of March 2022, as an example. That is now a summer season. That is what is displayed here on the x-axis. The y-axis is this just for different stations of the country, representative of the whole country, basically each time zone. And then the 4 different panels here is representative of 4 strong El Niño events. This year on the far left is the 1972-73, this is the 82-83 El Niño event, this is the 1991-92 El Niño event, and then this is let's call it the youngest strong El Niño event, between 15-16 El Niño event. So, again, considering this is on the y-axis with different stations, so here we can see that there are certain parts of the country, and these stations here are basically located in the western and central parts of the country. During all of these 4 different strong El Niño events had the occurrence of, or quite a few high occurrence of heat wave days. But then again, even within ENSO, one gets variability for these strong El Niño events. Here by 2015-16, the spatial and the temporal extent of the heat wave days were much more than compared to the 3 other ENSO systems. This is just to show you the state of or the oceanic mean index during those 4 years. So, message again, the weather over the country is really very, the climate variability is anyway there. So, how to cope with that? How can we within that variable climate and now with the extremes on the increase, better prepared for means of forecasts? Okay, so part of early warning, for some purposes, just a few days in advance is not enough for the appropriate kind of large scale kind of actions when it comes to be prepared. So we're looking at more about a few weeks in advance. So now if we look at specifically in heat wave days, trying to forecast that, and here this is up to 8 weeks into the future. So we divide it up into weekly periods. So just to summarize this, what this slide here shows is that somewhere between 1 and 2 weeks into the future, skill in predicting the occurrence of heat wave days, that is occurring it, and in this specific skill assessment, where the heat wave took place was also taken into account, it significantly drops. By week 3, based on this specific setup of this prediction system, and this was based over a period of 1996 up to 2009. Again, for that summer half year, 3 ways into the future, we just can't predict whether there's going to be an event like the one we just had now over the last 2 or 3 weeks. This is now this is now based on one of the best models, the UN, the British prediction model. That's one message. If we really want to use it, after 2 weeks, it's at this stage not really of any help. Now, this is the system we currently have in place at Source of working on our operational, this state's experimental operational maximum temperature sub-seasonal prediction system. In this system, we only go up to 4 weeks into the future. This is now a result from 2 of the models that makes part of that multi-model ensemble of this prediction system. This is the week 1 prediction, and in this case, the bluer it is, the better the prediction is. So here again, the message by week 2, I can already see quite the blue shade becoming quite lighter and even becoming orange or reddish in some areas, meaning that is still predicting, and in this case, not heat wave days, but the average weekly maximum temperature. By week 3, in both of these models that makes part of the multi-model prediction system, the bluish colors is for all practical purposes gone, or very light in shade, and if you look at those correlations, typically one would like to see a correlation of more than 0.6 in order to consider it as a forecast that can be of use. So again, the message after 2 weeks, not much hope. That assessment was based on a 1-year set of predictions, of operational predictions. Okay, so now going to end this talk off, conclude it with looking at 2 case studies. And for that, we're going to look at the 22-23 summer season. You can maybe remember at the start of the summer, we had quite a heat event. And then, of course, the one we all saw recuperating from.
we're going to look at how did the soil subsequent prediction system play in predicting that kind of heat event. And in this case, again, it's not heat wave days, but rather the average temperature for weekly periods. Okay, so just to set the scene for the 2022-23 prediction, let's just quickly go back. And now I also refer back to Charlotte's presentation. You can remember there in one of her slides, 2015-16 summer really sprang out in terms of the number of record-breaking temperatures, maximum temperatures. So indeed, and this again is an analysis on heat waves. You can't really see it, you just will need to trust me. But during the month of October and December of 2015, for those 9 different weather stations of the country, which is source weather stations, the 2015 month, basically in terms of the anomalies observed compared to climatology, really stood out in terms of how hot it was. Sorry, the mouse just disappeared there. Anyway, this is on that graph. On this graph here, that is now the heat waves, the number of heat waves relative to climatology. And again, on the far right-hand side, here is the 2015-16 summer season. So there you can just see that really reddish colors indicative of in terms of the frequency of heat waves during that specific summer. It is quite notable that it is really more a higher frequency spatially as well as compared to a historical period. If I remember correctly, that started in the 70, 71 summer seasons. That's quite over a large, quite a number of years or decades actually. Here on the right hand side, now we are back to 2022-23. Here on the left hand panel is the maximum temperature anomalies for the month of October, November, December, October, quite hot relative to climatology. Then, as everyone maybe had forgotten, November we had some cool conditions actually relative to climatology or than normal and over quite large areas of summer rainfall region, as well as during the month of December. That is just maybe one. This is not quality control yet. I got a suspicion about that specific station, but anyway, in the general area, cooler than normal. Rainfall wise, we had to start slow to the summer rainfall season, but then once it got going in November and December, most of the country we had quite above normal rainfall. Okay, so now the specific warm spells for the 2022-23 season, the predictions that we're going to look at. Yeah, just to show you, it was more or less, well, not more or less exactly, the first half of October. This is just me for choosing 3 different radio stations of the country, just to show that okay, that was quite a warm week. This is based on 7-day moving averages. So there was quite a warm spell at the beginning of October. And now on this side here is now for January. So here we can again see the 7-day moving average of maximum temperatures, what it looked like. And again, they're not these in terms of the departure from normal temperatures. For the January heat wave was between, let's say, 4, 5, or 6 degrees above normal. For the 2015-16 summer season, it even went up to 9 degrees Celsius in some areas. So just to give a perspective in terms of the magnitude, and even though we really felt like we were dying now, in terms of the anomalies, temperature anomalies, it was not as extreme as during the 2015-16 anomalies. Okay, now we do the forecast. So I think it's only 2 slides left. Okay, so this is now the prediction of the warm spell at the start of the 2022-23 summer season. So that's let's say the 1st of October. Just to give one again perspective of the heat during that stage. This is the weekly temperature anomalies. Here on the top is for the week prior to the week of 2 to 8 of October, which is this image here. And this is for the 9 to 15 of October. So I can really see that over a large part of the countries had warmer temperatures that exceeded more than 5 degrees warmer than normal. So it was quite hot, and then a little bit of cooling, so hot. Okay, but now looking at the predictions. So how can, what, how did, was we able to predict this kind of temperature anomalies that occur? Okay, so for the sub-seasonal timescale, we will typically look at forecast of 3 and 4 weeks into the future. Just to know what happens before that as well, is also good to look at the week 1 and week 2 forecasts. But if we here look at the week 4 forecast for this specific week, here over the eastern parts of the country, actually cooler than normal temperatures. Here over the western parts, okay, warmer than normal conditions are predicted, but if we look at the anomalies, it's at the most 3 degrees above normal. Whereas in fact, it exceeded in some of those areas more than, and this is just what's been on this image here, at least more than 5 to 6 degrees Celsius than normal. So the magnitude was not actually near enough, maybe to give an indication of the extent of the kind of event in terms of the magnitude of the temperature anomalies. But I must say I'm quite impressed at least that warmer than normal conditions was predicted, but nothing that will flare and say, hey guys, we only look at something really odd is going on. It's not saying that. This is quite enough for the week 3 forecast, one had a better indication. But then again, you win some, you lose some, then in the western parts of the country, actually there towards the Kakamas areas, no indication of an extreme heat event for that week. Okay, the week 1 and 2 forecast, we're not going to discuss to interest in time, but even the week 1 forecast, the magnitude of the anomalies is not indicative of something that is really trying be on the alert. Okay, so for the week of 9 to 15 of October, more or less the same story, or the message stays the same. Again, I'm quite impressed that at least for half of the country, warmer than normal, or hotter than conditions were predicted, but the magnitude of it did not really tell us to be on the lookout. Okay, let's now look at the most recent warm spell of this heat wave event of January that lasted nearly about 3 weeks. But okay, let's concentrate here on the week of 8 to 14 of January. Again, just to give an indicator or give some context, with a really wet December, which was definitely quite wet and cool in large parts of the country, cooler than normal. During the first week of January, that rainy and cooler conditions continued. Then this second week struck, the 8th to the 14th of January, and then 15th to 21 of January. The heat during the 8th to 14th of January was concentrated here over the extreme western and southern parts of the country. So now if you look at the week 3 and 4 forecast, for the week of 8 to 14 January, there's no indication at all of this week to be expected. Nothing. For the week of 15 to 21 January, the week 3 forecast, if we have looked at this forecast at that stage, one would think, nothing wrong with it. We're in a La Nina event, it's been raining cats and dogs for basically 2 months. Why not continue? So, yeah, cooler than normal, better. For this week, by the week 4, some indication of warmer than normal conditions, but again, the magnitude of it not shocking, being on the alert. And this kind of predictions, we actually want to employ in a manner that one can also be more alert when it comes to the short range predictions. Because as Charlotte has also mentioned in some other talks, maybe informal talks after crunch was really terrible accusations and source. And his thought, they are much more than just the predictions itself that needs to run smoothly. So as part of source, as part of our in-house process, also to be, and what we do at source also feeds into disaster management activities. Yeah, so in that sense, this is what we are doing behind the scenes to try and be more alert for this really extreme events. And there is a concluding slide, which I will just skip now. Thank you.
Thank you. We really got like 1 or 2 minutes. I'm gonna allow one question each, one for Charlotte and one for Christine. Here we go. There's one over there, and then we'll carry on after that. Thanks.
Charlotte, I just wanted to ask from a civil engineering perspective, as someone who is a training professional, I just wanted to know if you are working with, let's say, COC, when it comes to your variations in the report. There is the term periods that are being used when you design infrastructure is based on stationary data. So I feel like we are not in sync with each other. Or if an option was to retrofit an existing stormwater system, what would be the rainfall that I would have to use in order for cities to be more resilient?
That's a great question. I agree with you entirely. And I think I do mention that in terms of the fact that our building code needs to be relooked at, and we actually have more closer chat in order to improve those building codes. I know in terms of wind, the wind and the built environment have very strong collaborative work with sort. And so for wind, it's definitely being done, but not so much for temperature and for rainfall. So maybe you can lead the charge on that and bring us into that space. We'd love to.
Thank you. One more question. Okay, Marebo.
My question is for Dr. Bispo. About the business my question is for Dr. When you mentioned about the prediction skill for the pupils, is that after 2 weeks they this skill like significantly decreases? I just want your opinion. What are measures that are in place to improve that? You guys maybe have measures to improve the prediction skills for your models, and I think that would really play a huge role, especially from a public health perspective. Please be useful.
Hold it right into your mouth. That's how it works.
Yes, we do have plans to explore skill further. So when it comes to heat waves, and I think maybe what these case studies, especially the case study of or the data of October, have shown us that with 3 and 4 at least had the direction of the sea level in the right direction. So, and I think they compared to the January originally, if one gets the, or I really have high hopes that when the atmospheric circulation is applied more directly into the prediction system, that you will be able to, for specific kind of events, extend that skill plan. And I'm really confident that that will be the case for heat waves. So when it comes to rainfall events, I'm not that confident. But specifically for heat waves, I'm actually quite excited to push the boundary of the skill into the things on a more consistent basis.
Okay, thank you very much to both of you. We are gonna get 2 video inputs from colleagues that couldn't make the meeting. This one is from Professor Jimmy Adegboke. Some of you will know him. He was some of our boss some time ago. This, I think, is focused on the flooding that occurred in Nigeria, which I think is really important for us to consider. And then following that, we'll have an input from Isidine Pinto, who is online, I believe. Jimmy is not online. I just want to say that if you want to make a plan by sitting on the tables and moving chairs, go ahead, make yourselves comfortable. There's a spot here. And I also want to stress that the most and equally important part of this session is going to be after tea this afternoon. So please come back for that if you are not going to attend all of the session. We need your input on what to do about all of this. Okay, so
Sorry,
yes,
got 2 spaces in the front here.
okay, there's some spaces in the front. Right, here goes Jimmy.
Hello, friends and colleagues. It's a pleasure and a privilege to be in your company. Remotely this time, or virtually this time. I wanted to be in South Africa with you in person, but I'm unable to do that at for this particular meeting. But I'm delighted to be here, and I want to thank the Access leadership, Neville, for and the conference organizers for extending an invitation to me. So I'm going to speak today on extreme precipitation dynamics and the impacts of changing climate in coastal West Africa. I am Jimmy Adegboke. I'm a professor in the Department of Earth and Environmental Sciences at the University of Missouri, Kansas City. I'm currently on leave from Missouri, and I'm working at the African Development Bank in Abidjan as a senior consultant in the climate change department. All right, so today I'll be speaking to you on extreme precipitation dynamics and impacts of changing climate in coastal West Africa. This is work that we've done over the years with a number of colleagues, including some that are seated in this audience today. And so I acknowledge them, and I acknowledge our partnership and collaboration over several years and various topics. Okay, so let me quickly give an overview of what I intend to talk about today. So 2022 and 2012, 2 years. Last year and the previous 10 years before that. Major floodings. I use that to set the scene. Then we look at a couple of flood events across West Africa as well, and a study that we've done in that regard. I spent a bit of time trying to paint the landscape of the drivers of rainfall and extreme precipitation in Africa and West Africa. And then we would look at some results, just a few results from some of the modern studies that I've done. And then I will conclude with a few talks about how we manage this problem, how we deal with this kind of situation. So 2022 major flood in Nigeria. The devastation was extensive. The loss of lives and loss of property. Over 600 people died, and about 500,000 homes were destroyed. And so what you have really is what you see in this composite satellite image here. So in Nigeria, you have 2 major rivers, the River Niger and the River Benue. The River Niger is on the west side of the country, flows into Nigeria actually from other West African countries, on its way to the Atlantic. And then River Benue comes also from our neighbors to the east. This is Cameroon. And then, both rivers meet, in the middle of the country at a place called Lokoja, and then head southwards into the Atlantic Ocean. And so they form this Y-shaped circle in the middle of the country. So you have this imagery to the left, which is free flow, and then self-explanatory, the imagery to the right, the inundation, massive inundation that you see. This is what that means on the ground. This is 2012. Major inundation and damage, and again we lost about 300 people in 2012. Okay, so what I want to, with same sort of images here of that situation there. So what I want to underscore with all of this, okay, is that these kinds of flood events, you don't expect them. It is a 100-year flood event. This is what hydrologists is called 100-year flood event. And so generally, you would expect that, okay, maybe in about 100 years, you get one of those. Ballpark. I mean, that's not a scientific definition like a 100-year flood event, but that's what you expect. You tend to want to expect. Well, here's what happened in Nigeria in a 10-year time frame. We got two of those within just a 10-year time frame. Right. So what's driving precipitation in West Africa? Three things. Very clearly, one is the IT season, the seasonal, that's the intertropical convergence zone that responds to these seasonal surface pressure changes, so that's one. The second major driver is this interaction between the low-level African easterly jets in the middle atmosphere, and then you have the tropical easterly jets higher up in the atmosphere. Okay, so during the summer months, northern summer, during the rainy season, the ITCZ penetrates further into West Africa. And then because of that, you have this moisture-leaving air masses, that bring in all the moisture and the rainfall, to West Africa. So that's the rainy season. And then this time of the year, like January, December, February, is the dry season. All right. The ITCZ withdraws further south, closer to the ocean, and we have the penetration of this dry, usually dusty, and often cold winds that come south all the way from the Sahara Desert region. Take over most of West Africa and very little, except for maybe just a strip of land right by the ocean where you have some rain there. Okay, so basically that's what you have. You have the interaction between the intertropical convergence zone. This is an interesting diagram here. I will explain it other than to say that you can see the ITCZ to the left here. You can see in the middle atmosphere here the African easterly jet and how it interacts with the tropical easterly jet as well. So there's a very complex web of interaction between these three major drivers or factors, and then what it does is defines for us the dry season and the wet season. During the wet season, the tropical easterly jet is a lot more stronger, and this indicates that. But I just want to draw close attention to this, what you might think of as the four modes of rainfall in West Africa. And this is tribute. This is from the work of Sharon Nicholson, who's done a lot to help us understand rainfall dynamics in this part of the world. Okay. And so you have this negative positive sort of signal where the coast is sort of wet and dry, and the central parts of West Africa is wet. That's where you have a shift in this weekly lines that you have in this diagram here, the top left here. I'm talking about this top left panel here. That's the African signature. So you have a northward shift, and then that creates this situation where you have rainfall. In the 50s and 60s, when we had a lot of rainfall in West Africa, this is what you have, you know. But we haven't had much of this mode recently. And then you have a switch in the modes when Africa is sending jets, sort of shoots for the southward. And you have the coastal area is positive, lots of rain there. The Sahel region for the north is negative, it's dry. So that's the second mode. And then you have this plus situation where all of West Africa is experiencing an above normal rainfall situation. That's this plus mode there. And of course, we've had some very devastating drought events. That's this negative situation. Where there's just no rain at all across the entire region, the collapse of the monsoon system, really, is what we're seeing there. So I'm going to, this is a fairly complex picture here on the diagram here, but all this is saying, okay, is that the rainfall regime is also driven by factors that originate in the oceans, right? So the two teleconnections play a role here. There's an ENSO signal, you know, that is evident, but there's an even more an even stronger Atlantic multi-decadal oscillation, AMO signal, right? And if you look at West Africa very rainfall regime very closely, you will see that there's a bit of a phase shift between the AMO index and rainfall. And so when you're getting into a period where rainfall is going to be declining, you will see that signal first in the AMO. So there's some predictability right there, which has been discussed extensively in the literature. Okay. So what we did with a couple of colleagues was look at all of West Africa and flood events, recent flood events. And this is where I was executive director at the WASCO, West African Center for Climate Change and Adaptive Land Use. We published this book, 10 papers in that book, 10 chapters. Addressing various aspects of intense precipitation and floods in West Africa. So if this is something you are interested in, look for that book, please, and then you will find it helpful. The study that I led, one of the chapters that I led, apart from being the overall editor of that book, I also led an observational study using satellite data on the rainy season of 2017. Well, what did we find in that study? Okay, we found that, remember I was talking to you about modes, right? Where we have plus modes where we have rainfall in both in the coastal, above average rainfall in the coastal and in the interior parts of West Africa. That's exactly what happened in 2017. We showed very clearly.
Something happened. I don't know what.
That's exactly what happened in 2017. The second study was at the CSIR. I was mesoscale convective systems. We were able to see that very clearly in the city. And so, with a number of colleagues, this study that I'm referring to right here was led by Francois, who was at the CSIR. I was also there at the CSIR. It looks like just a few years ago now, but that's over a decade ago, really. Time flies. So this study, along with another study, and I'm just going to go on very quickly. We looked at both precipitation and temperature and looked at various indices there in terms of future projections. Okay, the second study was led by Babatunde Abiodun, who is a professor at UCT in Cape Town. And that study looked at climate change impacts on extreme precipitation
Another,
for African coastal
give me a
states.
coffee latte now.
So,
Okay.
what did they find?
It's a lot of coffee.
The
Coffee
earlier
latte.
study I saw was actually the continental-wide study. Okay, and several important results came out of that study that have very widely cited across the field. But let me just say, okay, that what are some of the key things that we found in really most studies, but more particular to the latter study that I talked about where we looked at intense precipitation. So the annual rainfall is projected for most of West Africa. You know, so that an increase, right? But there's an indication that you have a decrease in the number of rain days, while you have an increase in extreme rainfall intensity. So that's the key takeaway there, you know. So the number of rain days might decrease, you know, but the periods when you have rain, the probability of having more extreme rainfall days is high. You know? So that is one key result from that study. So let me end by saying, what do we do? What do we do? You know, my position here, as is that of many of us who work in this field, is that climate change does pose a really existential threat for communities across West Africa. And it should be a major concern for all policymakers, both the public and private sectors. And so we need to look at how our national programs see how do we make further investments to increase resilience and reduce vulnerability to the impacts of these types of events. Well, I suggest that some of those investments needs to be made in strengthening national and regional capacities to observe observational systems and capacities that we across West Africa. Those needs to be strengthened and expanded and made better, and then improve also the analytical, the modeling capacity that will help us even predict better these events as they occur. Right, and I'm going to wear my hat now as a development person at the African Development Bank and say that part of what we need to do and what the bank is really advocating for and trying to incentivize is what we call climate smart infrastructure. So embedding climate sensitive considerations into how we, you know, our infrastructure development life cycle, the entire life cycle of these river developments across not just West Africa, but really across the continent. And so the last point here is that extreme precipitations will be more common. They will be intense in the future over West Africa. And this poses a serious challenge that requires all of us to put our hands on the plow and figure out how to do this better and how to prepare for this better and to address these changes. Okay, so I'll end this here.
All right. Let me use on WhatsApp. I don't know if it's online. Can we see if it's online? There's our team. Isidine is there, but not Jimmy. Isidine, oh, is Jimmy there? No. Isidine, are you there? Can you hear us?
I can hear you very well.
In that, Jimmy is not available. We're going to move right along. In that case, to Isidine's presentation, which that done.
Hello, everyone.
Hi.
Is it Pinto? Unfortunately, I was not able to be present in this conference, but at the end of the,
One second, please. Izzydeen, if you can hear me, check your South African WhatsApp. Izzydeen is currently in the Netherlands. He was a PhD. Oh, hello, testing. Never mind. Izzydeen is a PhD student at UCT, access student actually. He's also an author, co-author in IPCC chapter 11, I think it was the IPCC report on extreme events. One of the lead authors, I think. And he's now working in the Netherlands, but this is research in South Africa.
the presentation. If you have any questions, please feel free to email me through email, which is visible on this presentation. So I'm going to talk about the climate change exacerbate.
Hold on. Figuring it out.
Yeah,
Okay. Okay, you can hear us.
Yes, now I can hear you.
Yes, very good.
Yes, now I can hear.
Ah, there you are.
Also note, please try to make sure that you would rather share the content on the PC
All right.
instead of on the camera.
Back to the, This seems to be the video. It's the video.
Sorry, we not get your question. You want me to
No,
start?
no.
Rainfall causing devastating floods in eastern South Africa. So you might remember, it's still fresh in our minds, that in April, South Africa experienced catastrophic floods and landslides in the eastern coast of KZN and Eastern Cape. And this was followed by these floods and landslides were caused by heavy precipitation events over 2 days. And these precipitation events were caused by a beta-flow low pressure system that was situated over the eastern parts of the country. And during that time, the South Africa Weather Service has issued an orange level 8 warning with the possible impacts of this particular event. And the president of South Africa has called the floods a catastrophe of enormous proportion and the biggest tragedy we ever seen, and declared the national state of disaster on Monday, 18 April 2022. This particular event had very negative impact. It caused the death of 448 people, more than 40,000 people are displaced, and more than 12,000 houses completely destroyed, and damaged infrastructure, in this case roads, health centers, schools, and various. And this particular event was in the news, and it was a very catastrophic event. And until now, there's this news, rewind of 2022, KZN still recovering from April floods that left thousands of homeless, destroyed lives and livelihoods. And there was another news, there's lots of news about this particular event. And also in the news, there's always this question, is it a consequence of climate change? So this particular presentation, we are trying to answer these questions that a lot of people always want to know after an event happening. So this particular study was a collaboration between various colleagues and scientists from the World Weather Attribution, and this report has been published last year in May. So what we do in this type of reports, we try to do a rough extreme event attribution to answer the questions if a particular event was made more likely due to climate change. But before that, we first do the detection analysis and observe the data set and observe station data set to see what is the amplitude and the trend of the specific events, and to see if the trend is also outside nature variability. And the attribution involves using historical and climate models data to analyze to what extent the detected trend is attributable to climate change or other factors. And in this type of studies, we use the peer-reviewed science and data that is readily available. And there's a protocol on the World Rate of Attribution. And as I said before, this was a collaboration between the KMI, Imperial, Red Cross, University of Cape Town, with the South Africa Weather Services, and other local scientists. And during this protocol, we look at the impacts of the particular event, data analysis, observation models, we do a vulnerability and the exposure analysis, and at the end, we communicate the results to anyone that is interested. And in this particular presentation, I'm just going to focus on the data analysis and observations and in the models. So before we dive in, it's interesting to just give a simple overview of what attribution is. So in this case, we have a climate response variable, and this variable is dependent on the internal variability and also model error and natural forcing and anthropogenic forcing. So this response is depending on 4 variables in this case. And in the attribution studies, we are mostly just interested to know the anthropogenic forcing. How does this influence this climate response variable? And then in this case, we look at the counterfactual world when the global climate was 1.2 degrees Celsius cooler than actually. So this corresponded to pre-industrial period. So we compare the world without anthropogenic forcing and the world with anthropogenic forcing. And to do that, we calculate the probability due to climate change of that particular event. And for that, we compute the probability in the present climate, we call P now, and we compute the probability in past climate or counterfactual climate without anthropogenic influences. And in this case, is in a world where global mean surface temperature was 1.2 degrees Celsius cooler than actually is now. And we calculate the risk ratio, the probability of the event divided by the probability of the event that happened in the alternate world. And we compute the uncertainty margins of risk ratios to see whether the risk ratio is different from one end at some confidence level. And it's also important to revisit the risk framework, or as we call the recipe for a disaster. We have the hazard, in this case for the particular KZN, the Eastern Cape was the heavy precipitation event, and we also have the vulnerability of the population in that area. In this case, the KZN, the population was vulnerable to that particular event, and the exposure that the population was exposed to the event, to heavy precipitation. And this caused the floods and landslides and so many other impacts. And in the attribution, because we do not attribute the floods or the impacts, we focus on the hazard itself. And then in this case, is the heavy precipitation or rainfall that caused the floods. So in the attribution, we are only focusing on the rainfall events. So in this case, the rainfall event that fell during 11 in the 12th of April is shown in this map, and in the red area is our area of interest. And we are going to analyze the maximum to the average rainfall in this particular area of interest. Before that, we analyzed some station data that was made available from the Weather Services of South Africa source, and in this case, there's many stations showing upward trends and downward trends in annual maximum to their rainfall, and also there is some stations with enough data, with 80% of data available between 1950 and 2022, and we analyzed the trends, and we found that for these particular 5 stations with enough data, they are not showing statistical significant trends. Only 2 stations showing upward trends and 3 stations showing downward trends, but not statistically significant. So therefore, we decided to use the AR5 greater data set to be able to do the area average for the area of interest. And in this case, this graph and the red line is showing the internal variability of precipitation on that region, and the green line shows the 10-year running average. And the event of the year 2022 was 36.68 millimeters per day. And what we do, we look at the precipitation variability compared to global mean surface temperature, and we plot the relationship. And in this case, we see an upward trend, but not significant, which means that the precipitation in that area is increasing with each global warming level. But as we see in this figure, is not statistically significant. And after that, we calculate the probability of that event. The event is 36.68 millimeters in a world that is 1.3 degrees Celsius cooler, and we compare it with the present climate. And what we found is that in the present climate, that particular event has a return period of between 15 to 25 years, so approximately 15 years shortening period, and that this particular event in a climate that is 1.2 degrees Celsius cooler has a return period of approximately 40 years. So after that, what we did is do the same exercise, but using the climate data. So from the model data, we do the same exercise for each model to come up with these return periods and the probability ratio between the world that was 1.2 degrees Celsius cooler and the present climate. And this is summarized in this figure, the probability ratio for AR5 data set, and for each climate model that we use the IRESNIP data set, we use the Cortex after the 22 degrees data set, we use the AMIC data, 10 ensembles, and we use the floor models as well, historical. And before we calculate these probability ratios of these data, we first evaluate the models to see how well the models simulate and replicate the climate of that particular region. And these were the models that passed that evaluation step. Once we do that, we calculate the synthesis, so we combine all the model data and the observations to come up with the probability ratio. In this case, the probability ratio between the past climate and the current climate is 1.5, and uncertainty between 1.3 to 2.1. And we also calculate the intensity change, so the intensity of precipitation in the current climate and the intensity of the precipitation in the past climate, and this intensity change is given in percentage. So in this case, the change in intensity corresponds to 5.5%. So this means that precipitation has increased its intensity due to climate change or increase in greenhouse gases. So concluding, we concluded that extreme rainfall episodes such as this one, this 2-day maximum rainfall, can now be expected to happen about once every 20 years. So here we approximated the 15 years to 20 years. And to say that without human-caused global warming, such an an event will only happen once every 40 years. So it has become about twice as common as a result of greenhouse gases. So this means that the heavy rainfall event that can now be expected about approximately once every 20 years is about 3 to 7% heavier than it would have been without climate change. And just to finalize the last sentences from the IPCC 6 assessment report, that states that the heavy rainfall is projected to increase further with warming following the closest temporal relationship on average, but with several regions. For example, East and Southern Africa is expecting to see higher rain rates, especially on daily and shorter time scales. So this was our conclusions from this particular market attribution studies. And thank you. And if you have any questions, please don't hesitate to contact me. Thank you.
Yes, is it Dean? You are there. I'm going to tell you that your talk was actually introduced this morning in the plenary session by Francois, who's in the room here. He mentioned your work. So you had a good introduction. Sorry, can you hear me now? Yes, okay. Just to say to you that that your talk was introduced this morning by Francois in the plenary session. He mentioned your work. We're just on time. To see if there are any questions in the room while Isidine is online. I do have a question. Can we just bring in the microphone? Okay, you'll take it. Yeah. Thank you. Sorry. Right, there's a question at the back. You can't see who it is. How do you introduce yourself? Christian. Leuma.
Thanks, it was a brilliant presentation, but I have a comment and question. I think looking through the risk framework that you presented, but it comes to my mind that climate change is one of the factors that justify now in person. So there is a vulnerability that we are also taking as a part of the fact. So I think in terms of adaptation and resilience coming to the threat to the community, we have to separate the impact of climate change today. The rain, precipitation probability, and we have done that. I think that was really your effect. And but taking this to the aspect of cloud, there are many factors that can justify cloud in the city. I would like to take, for example, infrastructure that can help water running in the city when it's raining. I would like to talk about the factor of soil capacity to absorb water during the rain. So this these are the factors that should be connected to should be considered in the model. And the question is that in your probability, as much as there is increased probability of precipitation, we should consider also that temperature is linked to possibility of probability of the rain. For temperature, that is not increasing linearly. It's the variation. So are you included in your consider in your model that non-linear progression of the temperature?
Is it, I don't know if you've got all the question, but you can answer some of it. And then I just want to say that a lot of what you've raised, we will be discussing this afternoon. But please go ahead, Isidine.
Yeah, thank you very, very much for the comment and for the question. Just to say that vulnerability and exposure play a huge role in a disaster, in this case, the flood and landslides. But for our attribution study, we only consider the hazard, which is the rainfall that causes the impacts for the flood. We are not considering the vulnerability and exposure in our analysis. And yes, we consider the extreme rainfall changes with the global mean surface temperature. There was a graph that I showed in the beginning where we have the changes in rainfall based on global warming levels. And in this case, we saw an increasing trend, but not statistical significance. So we take into account the surface temperatures in our statistical model to do the attribution study.
Thank you. Thank you, Zidane. I just want to say in response that connecting up all the dots from the prediction of the weather system and the climate system's responses all the way down to managing runoff and predicting runoff and managing drainage and its impact on people are really the end-to-end process of managing floods. And the same would apply to other kinds of extreme events. But in defense of the climate scientists, what they're trying to do is predict the climate for part of that whole story. But that's certainly something we're going to talk about. I need to move on. So Isidine, thank you very much. You're welcome to stay on.
Thank you.
I need to bring up the next speaker, who is Abu Bakr. Right? Yes. And you know which one? It's here. Yeah. Here we go. And then we'll break for lunch after this talk, but don't go away. I've got an announcement to make at the end of this presentation. Thanks. Yeah, thank you.
Good afternoon. Still morning or afternoon?
I think it's afternoon.
Good afternoon all. Good afternoon all. My name is Abu Bakr Hadisu. I'm a PhD student under the supervision of Professor Francois Engelbrecht. And I'm here to present to you part of my PhD work. So my PhD, the generality of my PhD has to do with the climate modeling of rainfall over the Nkangala escarpment. But here I'm to present to you the extreme event precipitation between 1961 to 2021 over the Nkangala escarpment. So let's do the journey together. Now, we know that Southern Africa is being projected to become systematically drier and also very warm. And therefore, the frequencies and the intensity of extreme weather events is expected to increase. So my study area, like I mentioned, is the Nkangala escarpment, which is part of the greater Drakensberg escarpment, which is found. Is made of mountain system which are found within South Africa, the Lesotho, the Swatini, and yeah, on the South African end. So to do that, I put my objective is to investigate the extreme precipitation over the Nkangala escarpment for the period that I stated, which is 1961 to 2021. So I obtained my data from the South African Weather Service, which I collected about 36 weather station data, out of which only 24 pass quality check that I use for this investigation. Their daily rainfall data that I use. Then I also homogenize my data using the climatal system of homogenization. That will help me, since most of my rainfall data is skewed data, which is not normally distributed. So it is better for me to, in order to reduce lag, autocorrelation and lag the trending problem that is associated with precipitation data. So now the expert team on climate dictation of extreme events, which is an arm of the World Meteorological Organization, do come up with more than 44 different indices that you can assess extreme events. But in this study, I'm using only 12 of those indices, which is being recommended by the World Meteorological Organization. Now, these are a list of the indices which I use in this study. So the list, there are a lot of them. Maybe as we go, you look at when we are looking at the result, we will see them. So now, particularly, I'm just doing precipitation, so I'm not doing temperature, just precipitation in order for me to look at that. So the indices are divided into 4. Some of them are percentile indices, which can be the 95% distribution of rainfall above 95% percentile, and we stand for the heavy rainfall and all the extreme rainfall, which is above 99 millimeter of rainfall. Well, some of them can be duration and some of them are also threshold. So for the threshold, I use the rainfall which are above 10 millimeter of rainfall and 10 millimeter, 20 millimeter, also 30 millimeter. While for other duration, I use the consecutive dry days and the wet days also for the study. Now, in order for me to find the changes that occur in my study area, I use the non-parametric data analysis, which is a Mann-Kendall test, and also the sense slope, which was used to determine the changes and also to determine the slope of those trends that I got. And since then for that, I also have to present or to interpolate my data, especially over my study area, which I did, and I presented it here. This is the mean annual rainfall of the study area, which ranges between 760 to 130 millimeters of rainfall per annum. So now let's go to the result and look at what I have done based on the absolute indices and the threshold indices. Now, if you look at the maximum precipitation in a month, which is up to 1 day, that at least you have rainfall precipitation in 1 day, at least in a month, you can see that most of the precipitation in this is found within the western part of the escarpment and also up to the central part of the escarpment. While for those days which are between 3 to 5 days within a month, is similar for the 3 and 5 days. If you look at the those graph, those figure B and C, but they varies with the one that I have with A. So for the maximum precipitation threshold that we have for the extreme indices for 10 millimeters, 20 millimeter, and 30 millimeter, then you can see for the 10 millimeter is that it's almost within the escarpment that there is at least rainfall that we get, which is 10 millimeters of rainfall within the month throughout the period of rainfall. And we know that the Eastern Escarpment is part of the greater summer rainfall period of South Africa, which range from October to March of the preceding year, and is being controlled by the convective rainfall system that is bringing a lot of rainfall to the Eastern Escarpment, which is being regarded again as one of the water producing area. And since extreme events are expected to increase or to decrease, then that's why we are interested in that. Then if you look at the other things such as the simple daily intensity index, and also such as the consecutive dry days that we have over the study period, then you can see that there's inverse relationship between the consecutive dry days with the consecutive wet days. So the number of dry days are increasing. If you look at the graph spatially, you see that most of the spatial distribution of the dry days, the whole of the area is like dry, while just inversely with the one that is the consecutive wet days. Well, if you look at the rainfall, the threshold, which is 95 percentile and also the 99 percentile, you see that most of part of the escarpment do receive rainfall which are within 95 percentile, while only few part of the escarpment, such as the western part of the escarpment, do receive rainfall which are close to 99 percentile of the distribution. Now, to look at the trend analysis, the change, which I use the Mann-Kendall trend analysis for the extreme precipitation, then we will look first and foremost. Now, the first one, which is the 10 millimeter rainfall of the escarpment, you see that there is a decrease in the amount of days, the monthly, which we have 10 millimeter rainfall. So from the graph, from my slide there, you see the downward movement of the triangle shows that there is a decrease in the 10 millimeter rainfall, and most of which are not statistically significant, with exception of one station. Well, if you look at the 20 and 30, you see that there is at least an increase in the amount of the distribution of 10 millimeter rainfall and 20 millimeter rainfall and 30 millimeter rainfall, with the exception of 2 stations for 10 millimeter, for 20 millimeter rainfall, which shows that it is increasingly significant, while for the 30 millimeter, only 1 station shows that it is declining or decreasing, which is significant, statistically significant. So if we look at the maximum number of days that we have rainfall, which is at least 1 millimeter, then we see also there that there is an increasing, it's a mixture of both. In some stations we have is decreasing, while in some is significantly increasing, among which are such places like Newcastle, and Newcastle in particular shows that there is an increase which is statistically significant, that shows that the rainfall over there is increasing based on that. Then if we also look at other indices, that which all of them have different kind of implication for the farming system and also for the hydropower generation, which are found within the escarpment. Then if you look here at the number of if you look at the total rainfall, total annual rainfall, which shows in this figure 6, you see that generally speaking, all the rainfall annually is declining in the escarpment, so which is also a concern for management purposes. Now, then if you look at the simple daily intensity of the rainfall, then we see that not all of it's not linear across the station. That there are some stations which are statistically significant, while one station is statistically many of the stations are statistically not significant, but they are increasing. So, well, if we look at the number of the consecutive dry days and also the consecutive wet days, then we see that the consecutive wet days are declining, while the dry days are increasing. Well, because of high variability of rainfall distribution there, you see at the 99th percentile, most of the station shows that it is decreasing. So now this is your station-wise showing the summary of what I found. So statistically speaking, most of it, not all of them, that are only the maximum precipitation for one day in a month has increased significantly, while others have mixture of decreasing or increasing, which are not statistically significant. Now, I divided this data into 2 just to see the changes, and this shows the changes that occur within the period of my study. So, in conclusion, we know that the extreme event is happening within the escarpment, but at different magnitude, and while the total rainfall over the escarpment is declining. Yeah, thank you.
Question for Mbaka. There is 2, you've got time for 2, let's take those 2. Can you take the microphone down there? Thank you. Okay, go ahead.
So, thanks, Greg. Again, this is what's going on as the West State and if I
Season?
what seasons, why are you using? So why are you looking at the annual number of days, or was it during the summer season?
No, I'm using the annual days, the annual. Yes, and remember the escarpment belongs to the summer rainfall area, so rainfall only falls within from October to March. So yes, I did the no, this this classification is based on the expert team on climate mutation also. So it's not done based on the seasonal basis. So we look at the total annual of each.
But it's a consideration to isolate the summer months,
Yeah.
and look at those trends.
Yeah.
Yeah. Okay, thank you. One more question, I think we've got. Yes,
My question was after the question. Is it then advisable to use, annual releases for, rainfall?
No, it depends on,
Rainfall varies from day to day basis, it means to wide, yeah, to take an annual instead of maybe monthly, look at it monthly.
depends on what you want. The analysis is based on the daily rainfall precipitation data. But if you want to do that on monthly basis, I don't think you will use these indices. Okay.
You can bring, and I'm looking at this is the status indices.
Yes, I can.
we can hear you, it's just the mic.
Yes, the package calculates it as a on an annual basis of the. So I just don't want you to be making conclusions like whether the trend is significant or not. Looking at the wider temporal scheme.
Thank you. Thank you, Dr. Tommy. Can I propose that the two of you have lunch together? Thank you, but before you go, I think somebody's grabbed the microphone. Give the last question, then I have an announcement that we go to lunch. Thanks. Thank you.
Thank you very much. Thank you very much. My name is President Marshall, and I appreciate you. Why we should start that?
So just
Okay, from the beginning, yeah, in Kanjala Escarpment is part of the greater Drakensberg region, and also is an area with high variability of rainfall distribution, but it's also known to be part of the water producing area of South Africa. And based on the regional climate models that we have, and the global models that we have, they all have different type of projection for the area. So next phase of what I should be doing is that I want to compare this my result with what we have on our CCAM model output in order for me to see if which one is for me to see if we're able to do the verification carefully and correctly. Yeah. So the area is known is there are some abstraction point of water dams for most of dams like dams and rivers, which are important for the bioeconomy of South Africa. Yeah.
thank you, everyone. Okay. Now, we're breaking for lunch. I want to urge you please to come back after lunch. Start sharply at 2:00. Dr. Mary Jane Bopapa, the head of SAON, will be talking. She happens to be a climate scientist. So she's giving us a keynote address or a guest lecture, I think it is. And then we have 5 presentations. You would have all got one of these. If you haven't answered the question and are intending to not come back, which we will judge you harshly, then leave them in the front. If you have got them and take them with you, bring them back after lunch. You'll use those for the discussion, which is the critical part where we really need your input. Okay, we really need your input because we're going to make decisions on how to organize this community as a research community around extreme events going forward. So thank you for that, and we will see you after lunch sharp at 2:00. Oh, lunch is the same venue as yesterday.